For what we did in the previous section was to solve for the variable x. So we have one equation in one variable, and we were looking for the unknown x. In this case, we have a formula, if we will, or an equation with multiple variables that's most of the times used in applications such as chemistry, geology, physics, any other another engineering areas. So, and well, in this case, they're asking us to solve for a specified variable. So what do we have? P equals 100 e to the k x minus 100, and they're asking us to solve for x. Well, let me highlight the variable that they're asking us to solve for. So our target variable here is in the exponent, by the way. So we will then let me add 100 on both sides and leave the exponential 100 e to the kx equals p plus 100. And well, after adding the 100 here, well, we can keep isolating the exponential by dividing both sides by 100. And well, that's going to leave us with e to the kx equals p plus 100 over 100. And well, from here we may go about getting rid of the exponential. And well, you know what to do about getting rid of the exponential. So when we solve an exponential equation, we do the inverse operation on both sides, which in this case is ln. ln on both sides, ln on both sides, and we'll cancel the e with the ln. Kx equals ln of the quantity p plus 100 over 100. And well, we can get x by itself at 1, so we can divide both sides by k. And x will be then equal to ln of p plus 100 over 100, and that whole thing divided by k. Now, although this is the final answer, this one might be a little weird to work with because, well, we have a complex fraction. That is, a fraction contained in one bigger fraction. So if you think this is a little weird to work with because, well, no, never mind. So you might want to use properties of logarithms to write this in a nicer way. Notice we have the natural log of a quotient. We can use the quotient rule for logarithms. So x will be ln of p plus 100. And because the 100 is in the denominator, we need to subtract ln of 100. And that whole thing divided by k. And that's the answer to the solution to this equation. So let's look at another example. So for the next example, what's this? L equals 8.8 plus 5.1 times the logarithm of d. Well, in this case, they're asking us to solve for uppercase d. And well, so number one, how about we isolate the logarithmic term so we can then solve for d. So let me subtract 8.8 on both sides. And then, well, from here, cancel the 8.8, and that's going to leave us with 5.1 log of d equals L minus 8.8. And well, we have that 5.1 multiplying with the logarithmic operator. We could do the anti-logarithm, but not yet because we have that coefficient. So let's divide both sides by 5.1. And that's going to cancel the 5.1s and give us log of d equals L minus 8.8 over 5.1. And well, now that we isolated the logarithmic term, so we may go about doing the exponentiation rather on a base 10 in this case, because How do we know it's on a base 10? Well, because that's the same base as the logarithmic function in this case. No subscript, it should be understood that it is a logarithm base 10. So, let's see, let me continue here. That's D equals to 10 raised to the L minus 8.8. I'm going to do this division symbol like this over 5.1. And that's final answer. So, again, our result in this case is not going to be a numerical value like we did in the previous section. No, we're working with formulas from science, from physics, geology, chemistry. Like the next one, it's a formula from chemistry. For those of you who might have taken a chemistry class, maybe organic chemistry already, you may have seen this topic about chemical kinetics. It's the part of chemistry that studies the rates of the reactions, how fast the reactions occur. And well, one of the properties involved in those situations is what's it called, the activation energy. And the activation energy is the energy required for a chemical process to occur. And that what's it called, that activation energy, you may have seen it in a biology class. It's the same thing because essentially biological processes are also related to chemical reactions, all right? And so this is a formula for E, that's the activation energy for the process, for the reaction. Well, let's solve for K in this case. All right, so this is what we're going to do first. I'm going to divide both sides by negative RT. And well, that's to isolate the logarithmic term, the logarithmic factor. That's ln of K over A equals to E divided by RT. However, that has to be negative. All right? And well, so we may go about getting rid of the logarithm by doing the inverse, which is to exponentiate on a base E. All right? However, be careful. The exponential affects the whole thing on the right-hand side, while on the left-hand side, we just cancel E with ln. All right. So now that we got rid of the logarithmic operator, we are left with the quantity K over A. K over A, and that equals to E to the negative E divided by RT. So we can express it like a diagonal division to make it shorter and easier to write and read when we write these exponentials. And well, we're essentially one step away to get our K by itself, and that's we multiply by A on both sides. Cancel A with A, and that's going to give us K equals A E to the negative E over RT. All right. So again, that's basically the same as going back and forth between logarithms and exponentials and the like. And well, so now we're going to apply this to other situations, and that's going to be our next page in one of the first applications for population growth. Well, what we have here, so a colony of bacteria that grows according to the law of uninhibited growth is modeled by the function n of t equals 100 e to the 0.045 t. Well, how do we know this exponential function will represent growth? Well, look at the sign of the exponential factor in this case. Well, the exponential factor, it's positive, so that means we're going to be modeling growth. Otherwise, if the exponent is negative, what do we have? We have decay. And we can also look at how many bacteria is dying by looking at the decay function. But in this case, we want to know how much bacteria, the population of bacteria growing in this case, all right? Well, so in this case, they gave us pretty much everything. There's other situations in which we have to figure out the k in the k by ourselves, and well, this let's look at this one. All right. N is the amount of in grams of a bacteria, because well, it's not easy to count number of bacteria the same way it's easy to count number of people. Well, even with a microscope, there's no way to have enough scope to to count bacteria like that. So that's why it's counted in terms of mass, of grams in this case. All right, so determine the initial amount of bacteria. That is, when we read this initial, that means when t equals to 0. All right, that's the initial. That means initial. And well, all we do is evaluate this exponential function at 0, so that is equal to 100, e to the 0.045 times 0. And well, let's just simplify. That's 100 e to the 0 times a number, that's just 0, and 100 times e to the 0, that's just 1. So that's 100, and well, let's make sure we use the correct number, the correct units, in this case grams. All right, so let's see. What is the growth rate of a bacteria? Well, the growth rate of bacteria is given by the number that multiplies the number that multiplies t in our exponential equation. In a similar way that when we have that the slope of a function, the slope of a linear function, which is actually a measure of the steepness of the line, whether it's positive or negative. Well, in exponential functions, that number that multiplies the variable t, x, or whatever variable, it's actually the growth rate or the decay rate, as in a similar way as for it's sort of the slope, if you will. But well, we don't call it the slope in exponential equations. We call it growth or decay rate. And well, all we have to do is just state that value k equals 0.045. What does that mean? Well, we still need to interpret this result. Although this is just the decimal number, let's change that to percentage. So that's 4.5. Well, so this percentage is telling us that that for every value of t, the population increases by 4.5% with respect its initial value. All right, that's what it means. Now, what is the population after 5 days? Well, all we have to do here is evaluate at t equals to 5, and that's 100 e to the 0.045 times 5. Well, let's simplify this using our graphing calculator, and well, I get an approximate result of 125.2 grams. Well, and of course, you should get a larger value than the initial value, the initial population here, because well, we're talking about growth, all right? Now, how to do this using the calculator? Well, let me open my calculator here. And let's see, second quit. And so I'm going to do 100. And well, to get the exponential, what do we do? So we have the ln keystroke here, which has an exponential in blue. So do the second function, ln, to get the exponential, and just type 0.045 times 5 in this case. And that's where we get our result, 125.2. I just rounded it to one decimal place, but again, It depends on the instructions. When you guys are working on the Alex homework, it may ask you for 3 decimal places, 4 decimal places. Well, it varies. Okay, how long will it take for the population to reach 140 grams? So in this case, we will replace this n of t. Well, let me write down the equation. N of t equals 100 e to the 0.045 t, and have this quantity to replace n of t. Okay? Because that big N represents the amount of bacteria, in this case in grams. That's an amount of bacteria. And what's that? So we want to know this time how long will it take to the initial population of bacteria to become 140. So that's 140 equals 100 e to the 0.045 t. And well, this is going to take us back to those baby exponential equations we did at the beginning of the previous section, in which, well, that one contains only one exponential term or factor. So all we do is do everything we need to isolate the exponential, then apply the inverse of the exponential and finally get the value for t. All right. So let's start by dividing by 100 on both sides. And that's going to be cancel. And e to the 0, e to the 0.045 t equals, well, that's 140 over 10. That's essentially, let me reduce the zeros. That's 14 over 10, which can still be reduced to lowest term because it turns out that both numbers are even numbers. So that's actually 7 over 5. And actually, let me leave some space. You'll see why. E to the 0.045 t. So how about we do ln to both sides? We do ln to both sides because we have the exponential base e, the natural exponential. So we will do the natural log on both sides to cancel those two. All right, cancel them out. 0.045 t equals ln of 7 over 5. And finally, divide both sides by 0.045. And cancel. That's t equal to, well, ln of 7.5, 7 over 5 over 0.045. Well, that's our initial result as an exact answer. But again, in this case, we want to have an idea of how many, days. Well, that number doesn't tell me anything about the time it takes to the population to become 140 grams. So in this case, I need the graphing calculator to get the result for us. So that's going to be after 7.5 days. Now, how do we do this in the graphing calculator? Let's see. So that's what should we do? Okay, ln of 7 divided by 5. Okay, careful when writing the logarithmic factor here. So ln of 7.5, close parentheses, and then divide by the number 0.045. And that should give us the result, 7.47. So I rounded it to 1 decimal place. All right. For days, I think that's pretty much 7.5 days, essentially. Almost 8 days, Now, the question here is, what is the doubling time for the population? In this case, what's the time required in order to get the double, twice of the initial population? So in this case, initial population in this case is 100 grams. double of the population, that's going to be 200 grams. Now, we need to know the exact time in which we will have twice as much bacteria with respect to initial population. So it's going to be a problem like the one that we just did in part D. So again, let's write the equation again. N of t equals 100 e to the negative 0.05 t. And in this case, we want to know when is n equals to 200. Oops, 0.45, right? T 0.40. Where did I get the negative? Never mind. And 0.045. And well, let's solve the equation. Let's start by dividing both sides by 100. And well, that's going to leave us with the exponential e to the 0.045t equals to 2. And just take the logarithm ln of 2, ln on both sides. Ln of 2 on the right hand side. Cancel the logarithm with the exponential on the left hand side, and we're pretty much ready to solve for t. So that's going to take us to 0.045 t equals to ln of 2. And just divide both sides by 0.045 the same way we did in the previous part. And so that's cancel. That's t equals ln of 2 over 0.045. But again, we need to have an idea of what's the actual number. What's the actual number here? So ln of 2 divided by 0.045. And that's actually after 15.4 days. Right? And again, units matter in this case. Make sure to go with the correct units. So in this case, notice how we're using units of time, right? And in this case, we have to go with what's specified in the problem. So t represents the number of days. All right. So let's see. We have another example. So on the next page. So again, a colony of bacteria increases according to the law of uninhibited growth. All right, what is that law? In this case, notice they're not giving us any equation. In fact, we have to figure it out. Okay? So let's see. Well, in fact, we will not even care about the amount about the initial amount, and you'll see why. Well, check this out. So uninhibited growth, that's basically n of t equals n initial, or sometimes they use a of t for amount, equals a sub 0, that for initial. So n raised to the kt, and in this case, notice the exponent for the exponential is positive because we're still talking about growth. All right. So for growth, number one, for part A, if n is the number of cells, and t is the time in hours, the number of cells reproducing in a living being, for example, express n as a function of t. And well, again, I'm just going to repeat myself here. That's n of t. N of t equals n initial e to the kt. All right. So we're going to start with that and then answer a couple of questions. So number one, letter B. If the number of bacteria doubles in 3 hours, okay, let's highlight this. If the number of bacteria doubles in 3 hours, find the function that gives the number of cells in the culture here. All right. What does that mean? This happens. Okay, let's. This is a little cryptic, but let's write all the implications this sentence is actually giving us. So number one, this is telling us something about t equals to 3 after 3 hours. Okay, but what about it? So that's when t equals 3. That means that whatever initial population and sub-zero, whatever that number is, in fact we don't care at the moment, and we won't ever know. So that population becomes twice as much of that population. So that n initial becomes 2 times n initial, 2n initial. All right, which implies well, that's just the implication, right? Like in words, like the process, what's going on? Well, we need a mathematical sentence here, a logical sentence that represents this situation, so we can implement that in the mathematical model that we're working on. In other words, this means that all these ideas put together mean that n of 3 equals to 2n initial. All right? When t equals to 3, we obtain 2 times the initial population. So again, let's get started with writing the what happened here.